So Google search's output and what you see is a composite of the relevance and the importance score, and they both do play a part in the output that you see and the ordering thereof. But the importance score specifically determines the top results. So that determines the first page or so of results that you see. So the idea is that for the first 10 or 20 results, they all have to clearly be very relevant. So they all have to contain keywords. And then the question is, amongst those that contain keywords, how do we figure out which of them are the most important? Now, Google's ranking algorithm, we should point out, is called PageRank. And it's a clever pun on Larry Page, who was one of the founders of Google, so his last name there. And so an interesting Cornell study in 2008, just to show you why we really only need to look at the first page or so, that's why we focus on the importance score here in this lecture, is they searched typical nouns and they tried to see how many... They did a study on the number of clicks that each search result gets on average. So what fraction of the clicks? So if you're someone searching, how many times are you going to click on the first one? How many times are you going to click on the second one, and so on? So in all, if we took the proportion of people who click on the first link, the proportion of people on the second link, and so on, how does that decrease? And so the first link gets something like 56% of all the clicks, which is really remarkable. And it drops off pretty quickly after that. So we have 56%, 13%, 10%. That's up to almost 80% just from the first three results. So the first three results right here, they see almost 80% of all of the clicks. And the first page itself is something like 98%. So if we took the first page, that was about 98%, and I believe I have those statistics here as well. So the first three links receive about 80%, and the entire first page actually receives greater than 98%. And so these first three links in the entire page are really determined, so they're ordering amongst themselves. Once you have those relevant pages, those are determined by the importance score itself, and that's really what's going to play an impact here. So we will be focusing on the importance score in this analysis. So now let's move to understanding how the importance score is used to rank these pages. So the first thing we have to take a look at is the idea of a web graph and what that is. And we're going to see how this can give a connectivity overview of the web pages and how they're interconnected with one another. So let's start with some terminology. A web page, we've been using that term, but it's a document on the web. So it's a document, and you can go there and access the page and do whatever you want to do on that page. A hyperlink is a connection from a web page to a piece of data. So on the web pages themselves, you see some external links here that you can click on, and when you click on them, that'll bring you somewhere else. Now, typically, it'll bring you to another web page. So for our purposes here and what we're seeing, a hyperlink is a connection from a web page to another web page. So we have web pages, and then we have hyperlinks connecting web pages. Right. So now, before we talk about a web graph, and you could probably already understand what a web graph is, it's really just the web pages and how hyperlinks connect them together, and we just draw that visually. But so a graph is a huge concept mathematically, and we will not go into much detail on what graph theory is, but simple terminology here will suffice. And when we say graph, we're not referring to some like XY chart plot. That's not what we're referring to. We're referring to something, a structure, a mathematical structure that has nodes, which are also known as vertices, and those are represented typically as circles. So we have these nodes, and we have links or edges. So those are kind of interchangeable. So either vertices or edges, or nodes and links. And the nodes are circles, and the links connect the nodes together. So we may have links like this. So if this is node A, this is node B, and this is node C, then I have a link between A and B. I have a link between B and C, and so on. I may have a link also between A and C, but maybe not. And it'll depend upon how the graph is connected. And so now we can take this and we can apply that to a web graph, which is just a graph of web pages. So in this sense, now the nodes themselves become web pages, right? So we have web pages as our nodes, which we will still draw as circles, but the web pages become our nodes. So suppose we have just 3 web pages we're looking at here. And the links become the hyperlinks. So the hyperlinks are connected to them. So now, one thing that we have to make note of is that here we drew the links without any arrows or anything indicating a direction. Now, graphs can have directed links, in which case it's really only implying a one-way connectivity. So A may connect to B, but B may not connect to A, and C may connect to A, but A may not connect to C, and C may connect to B. For instance, B may not connect to C. So when we're dealing with a graph of the internet, or a graph of the web pages, these links are directed, because hyperlinks are only go one way. They don't, just because A points to B doesn't mean B is going to have a hyperlink back to A. So if this is page A, maybe page A has a hyperlink to page B, and then page C has a hyperlink to page B, and so on, something like that. So a simple example of that would be if you have a website and your favorite artist also has a website, right? So maybe this is your artist's website, this is your favorite artist right here, and this is you, and this is your website right here. Okay, so you may have a link on your page that goes to your artist's website, and there's a lot of other people that probably also have links that go to his website as well, but it doesn't mean that he's going to take a link and put it back to your page for every single person that puts a link to his page. So they're not bi-directional, and otherwise there would be a lot more people that were famous because they would just feed off of that and be able to gain a lot of fame. That obviously wouldn't work too well. But so now the way that we indicate a directed graph is by having the links have arrows, and as we said, a web graph does have directed links. Another thing about a web graph is that it's very sparse. By sparse, we mean that most web pages aren't connected to one another directly. So for every web page, a web page has a very few number of neighbors, which we call them. So if we look at a node A here, B is A's neighbor because A is connected to B, and so on. He can get to him in just one path jump. The number of neighbors that each node has is way smaller than the total number of nodes. So I mean, we have something like 60 billion nodes in the internet, right? So there's like 60 billion web pages, but the Wikipedia page, which is on the higher end of the number of hyperlinks you see, may have like 100 links out to different pages. So 100 versus 60 billion is much, much smaller. And so by sparse, we mean that there's not a lot of links compared to the number of nodes. And the internet itself, as we said, has 60 billion nodes. So that gives us kind of an issue here, because there's no way that we could ever draw the graph of the internet and then do like a calculation on that, because that would just take us our entire lifetime. We'd still never finish. So we're going to have to use examples here that are of much smaller scale with 4, even 5 nodes maybe, and look at those. But still, the ideas are the same. It's just done on a much larger scale. So the ideas are portable and they scale up very well. And Google has a lot of algorithms in place which scale them to very high data sets and very large data sets.